This is mainly important for counter is important for troubleshoot, diagnose your job. Okay, so this is important once your job is done, and counters will only be created when your job is successfully executed. If any failure happens in between and your job gets failed or uh, uh, not completed, so counter will only be created when your job is done, when your job is completed. Counter has many type. Counter has many type, but first, as always, we we discover why counters. Troubleshoot, shoot off job, and diagnose them. Okay, this is why we create a counters, and there are many counters. There are many counters. Job counter, task counter, user defined user defined Java counter, dynamic counter, retrieving counters, file system input counter, file system output counter. So these are your counter types. And as written as main headline, troubleshoot of job and diagnose them. So there are many parameter once your job is done, like total memory in, memory out, network in, network out, bytes written in heap memory, bytes read from heap memory. This information you will see you will see in your counters. Okay, and where you can see them. So counters are only created. Counters are only created when job gets when job gets successfully completed. Successfully completed. Now, why do we need and where do we need them? So, suppose you run one job today. You run one job today because obviously you're running daily jobs. Many tables are there which are running daily. So, one job today you're running, uh, and that job is taking 1 hour of time to complete. Then the same job again you're running next day, and that same job. So, this is job number one in today's date. This is job number two. Job name will be different, but data table, that information is exactly same. Now this job 2 is taking me 2.5 hour. So there is a difference between job 1 and job 2. Though they are same job, but why they are taking extra 1.5 hours? That part we will check. That part we will check with the help of counter. So counter will tell me problem is with environment, or problem with more data, that this job 1 is having less data, this job 2 is having more data. How do I know that? So when I check my total bytes read and write, I can see that how many bytes written for job 2 and how many bytes written for job 1. This information we will see in a bytes. Okay. When we run a MapReduce program, a Spark program, Scoop program, I will show you that how we can see these counters, where these counters are visible. Third problem, do we have any problem with our code? So error and exceptions it will encounter and display as a log file. This is why the counter is important. After counter, so just remember this point. The question if coming, what is the use of counter and how many different types of counter we have? This question can come. Then distributed cache. Distributed cache. What do we understand by distributed cache? If you see cache, this cache refer my volatile memory. Volatile memory means not a permanent storage. Volatile and non-volatile. Permanent storage is a hard disk, which we call a non-volatile. Volatile means non-permanent storage, which is a RAM. Distributed cache means, let me write a task. So if we see such task coming in our basket, first task says there's a file, there's a there's a file with a size with a size 100 MB. There's another file. There's another file with 10 GB size. Okay. Now 100 MB and 10 GB. If I want to perform a join operation, okay, join both the file, join both the file and retrieve retrieve common data. That's why we use a joining concept. Inner join, outer join, left, right, pull, self, cross. That all we have seen in SQL. The basic analogy of this joining. Where if I'm joining 100 MB file and 10 GB file, this will take a time because both I'm keeping in hard disk. My final storage is in HDFS. So this 100 MB data I will put in HDFS. This 10 GB data also I will put in HDFS. Then I will write a MapReduce program to process this data. Then I will define my number of map task, reduce task. But since the size of one file is very small and a second size of file is very big, it is recommended to use such concept for those data, distributed cache. And what is that concept? It says, can you do one thing? Can you save this 100 MB file, store in a memory? Can you store this 100 MB file in a memory? When I say memory, non-volatile, which is RAM. When I'm storing this file in RAM, when I'm storing this file in RAM, my process will, my process is not now, my task is not reading information this file from hard disk. So only one file I'm reading from hard disk and second file I'm directly reading from memory for to perform this operation, map side join and reduce side join. If I'm joining using with the help of mapper, I call map side join. If I'm joining with the help of reducer, this part we'll see internally in detail within Hive warehousing. So here we are here we are joining this two file. Here we are joining this two file, 100 MB file and 10 GB file. In Hive, we will join table because Hive is a warehouse. Hive does not take care of file. Hive takes care of table. So when you see table to table joining using map side join concept, you will be able to relate with your RDBMS. Here I'm joining a file. So I will write a program in MapReduce and write one task related to map only. I'll say that is a map side join. If I write a program only related to reduce, I'll say reduce side join. But why I'm doing such? Because if I'm doing this, then my hard disk is not having this 100 MB data. Actually, my memory is having this 100 MB data. So anytime reading from memory is faster than reading from disk. So my performance will increase at least 50% or 25% minimum if I use this. But one limitation is here. One limitation with a distributed cache, you have to have this smaller file and this bigger file. If you have 1 GB file and 1.5 GB file, I will not say this is small and this is bigger. right? I'll not say this is small and this is bigger. So I'll keep both in hard disk because I should be available that memory in my my cluster should have that memory available. Then only I can keep it. So if it is way less than one file, the second file, then we use such concept of distributed cache. Memory of this one, memory of your slave, obviously. Client is submitting the job. Client is only meant for submit the job. Master is only meant for monitoring purpose. Everything is done by slave. All uh, distributed cache, processing the task, in-memory reading, disk reading, optimization. Okay, everything is done in the slave side because all this machine. When you say slave, slave is also one physical machine, right? There we have number of core available, number of processor available, RAM available, tuning available. So everything is available in the slave also. So this will be taken care by slave. Out of many slave, which slave will be chosen? Again, the same concept, near to client. If client is trying to read the file or write the file, what your master does? Master will master will check the client location and based on that, it will sort it. So if client is trying to process the file, it will map which is the client, where is the client location, and whichever is near to that client. Suppose today I'm sitting in Pune, you're sitting in Bangalore, you're calling from Bangalore. This machine is we have many clusters, some in Bangalore, some in Mumbai, some in Pune. So your call when you submit, that process will happen in near to your machine, near to your client location. If I submit any job from my machine, it will go to near to my machine. That's the it is everything is following with the concept of data locality. So when you process it, when client is requesting to name node always maps the client IP and data node IP. Whichever data node is near, name node will give that information to client node and they start processing it. So everything is dependent on the client location, where client is located. This is in short distributed cache. And distributed cache, so since you're storing this in memory, again you will distribute this in memory. And again we can increase or decrease the size of, here I can say all 100 MB will go in one distributed cache only. Okay, or I can say 50 MB 50 MB. Just like in blocks we create 128 MB 128 MB, here also we can create 50 MB 50 MB or 25 MB 25 MB 25 MB 25 MB, four different map tasks. Only difference, only the way why my performance or program is faster, because I am not reading from hard disk, I'm reading from RAM. Reading from RAM is anytime faster than reading from hard disk. But only this concept is only passing through few conditions. If my one file size is very small, if second file size is comparatively bigger, then I will use it. If this is the example, 1 GB and 1.5 GB, I'll not say this is small and this is bigger. I cannot say that. Okay, so logically we need to see this. I have used once distributed cache and thin jar and light jar concept because my plugin was very high, very heavily, and whenever I want to copy that to my development cluster using WinSCP or FileZilla, it was taking time. So I use this thin jar and distributed cache concept to distribute my data and store in a RAM with one project, but not always required. This is a distributed cache. So in MapReduce, in short, we're done. Things to remember, again, I'll recap. Things to remember in MapReduce. Starting with how they are submitting the data, how distribution submission is working. Second, how your task is processed by node manager. Third, what if one task will fail, what will happen? Then what if your node manager fail, what will happen? Third, what if your job will stuck? Then fourth, how we'll create a MapReduce job, how we'll create a project in IntelliJ, how we'll take a plugin and dependency of Hadoop. Then we have seen how we will create a jar and copy to server using WinSCP. Okay, so till jar file creation we have seen. Then how we will use a compression technique, using what concept, then what is the number of counters, what is the input format, output format, and what is the distributed cache. This whole set of concept is from MapReduce. Now, this MapReduce is a programming model, and HDFS and MR both are your Hadoop component. So other services, like if I design my ecosystem, this is my storage layer, HDFS. This is my storage layer. This is my computation layer. We are talking about yarn. There's one more option many people uses it, mesos. Also, this is also designed by Apache. So mesos and yarn, this is a computation. This is for computation. We call this as a computation layer. Then third, we have uh, MapReduce. MR, we have a Spark. This is application layer. Application layer. These three layers are there in Hadoop. Okay, remember all the point. Currently, we talked about application layer, uh, Spark and MapReduce. But this application layer is ultimately reading data from where? HDFS. Now we are going to see this many ecosystem. We have Scoop, we have Pig. So all the names are related to air, mostly animal. Hive. There's also one flying creature. Uh, then we have HBase. This is way fast. So H table, uh, metaphor they used to have, that how NoSQL can work and how fast they can give you the query. So there is one benchmarking of Facebook. Facebook used to work with HBase till 2018. From 2010 to 2018, they used to work with HBase, and you know why? Whatever messenger talks you're doing in Facebook, so this messenger information is getting stored where? In HBase, because this messenger is low latency. You see how total number of traffic for Facebook per day is 17 cr. 17 cr people visit their website. So how much load they're handling, their server bandwidth, right? So all this information is getting stored in HBase. This is way low latency data. And if I tell you their performance, this is anyways freely available in the blog side again. Uh, I read this in a Facebook blog itself, HBase, and they process 1 billion. You'll amazed to see this number, 1 billion query, 1 billion query per second, using 2,300 nodes. Highly impossible in any of the RDBMS. Even we can't even think about it. So 1 billion query per second is achievable because of NoSQL and because of number of load balancer. We have balanced our load. We have distributed our data in all this machine, right? So similarly, LinkedIn has their own NoSQL currently. And if you want to read this, I think this information must be available in here also. Let me go and search in the Wikipedia. HBase Wikipedia. It is based on the concept of big table paper, Google Big Table. Google has played very big role in all this open source technology. Okay, where is Stockholm based database? Yeah, here's the point. Read this. Facebook elected to implement its new messaging platform using HBase in November 2010, migrated away from HBase in 2018. So, messaging platform, this is a messenger platform only. And after 2018, they're using their in-house service called Myrox. So, all these big companies which you see and often read, LinkedIn, Amazon, they which are handling with large data, they all work with this big data platform, big data tools, because their data size itself is very high. Anyways, so when I run anything in a Scoop, Hive, or Pig, they all are dependent. They all are dependent on where? They all are dependent on this platform. This platform is created by Hadoop. So when you run any query in Hive, so Hive is submitting their query to where? To MapReduce. But Hive is reading or storing their data to where? Hive is reading or storing their data to your storage layer, which is HDFS. Same thing goes to Scoop. Scoop writes their all the information where? In HDFS. And whenever they try to extract any information, where their query will go? To MapReduce. Pig query will go to MapReduce, where they will store their data again to HDFS. Same thing HBase. HBase will not use the MR. HBase as an individual. HBase is their separate in processing program written in a jQuery language. jQuery stands for Java plus Ruby. So this is a BV of Java plus Ruby, you can say. Using those languages, we have created this cell, but ultimately data storage is going where? Data storage is going here only. That's the reason we call this services as ecosystem. Ecosystem, because they are dependent on Hadoop. If this is down or this is down, you can't work with this. If your basic platform is down, you cannot do anything with this. Okay. Although Spark support, Spark support standalone system, cluster environment, and client environment. And nowadays, because MapReduce is becoming very tedious and complex programming, people started giving more focus on Spark, and Spark is very stable now, which can handle any program, any concept of MapReduce. So nowadays, they started changing their execution model from MapReduce to Spark. Just one reason: to complete the task as fast as possible, as quick as possible. That's the reason to change from this application to this application. Okay. We have already compared MapReduce and Spark. When again I visit Spark, I will recompare again. Do we have any other point between MR and Spark? So before going to other programs, we will first start extracting data from a Scoop. Why we will have to do that? Hadoop is meant. So uh, again, if you go to your observation, Hadoop is meant for what? Hadoop is designed or created. Hadoop is created for analysis purpose, for OLAP purpose, right? Analysis purpose or behavior. OLAP stands for online analytical processing. OLAP is online analytical processing. Analytical, one second. Processing, right? Now, so we are saying analytical processing, but to analyze any data, we need a data first. So this is my HDFS. This is my Hadoop storage. But from where I will get data here. This is my HDFS. From where I will get data. So let's do two comparison first. First comparison is historical data analysis. Historical data analysis. Historical data analysis means um, you have your data stored, 50 years data, 100 years data stored in your some server or some RDBMS, and you want to analyze that data. Analysis means maybe if I'm working with a real estate company, I want to analyze the inflation rate. How is the progress or growth rate of metros of India or sub metros of India or capitals of India? Okay, then I'll check. Okay, so is it good, because I need to talk to my client that you have this much capital, so you can invest to Pune, Delhi, uh, Vadodara, XYZ city. But before giving any suggestion to my client, I need to analyze it first. And to analyze this, you need data. Now my data is coming from upstream source. My data is coming from upstream source. What do I mean by upstream source? This is something web server, flat file location, some data point. Let's say you're going today, you're going today to powertech.in, and while practicing you have a query. So when you have a query, you go and submit your query here, your name, email, contact, subject, message, and you do this activity. You do this activity at once. You do this activity at 3 a.m. Let's say you're working late night, but nobody is sitting there, right? How they will get to know this information? From where they will tomorrow analyze this information and try to support you? So this information is connected with RDBMS. This data is getting stored in Oracle or MySQL. So when tomorrow office open at 9 a.m., people from support can open their site or whichever link they follow. They will see, okay, there are 5 queries, and based on the FIFO order, they'll start solving the query. But my question is, there is no foundation that you cannot go to this website at 3 a.m. or 5 p.m. This is open 24/7, and this is the case of any website. You can go to Amazon also, and you can purchase anything at any time. But when you're purchasing that information, where your final data gets stored. So this site is nothing but my upstream source. The site is nothing but my upstream source, which I'll refer as a web server. And upstream source will will write this data to where it is writing to RDBMS, which I can call as a downstream source. Downstream source. I'm trying to create a flow. This is what we do in companies. Whenever any historical data analysis, this is what is a standard flow. Any historical data. Okay. I'm not specifying the application, that it is only the banking application, healthcare application, real estate application, e-commerce, retail store, anything. You name it. If you have a data stored in this upstream boxes, you have to have you have to extract this data to HDFS using some utility. So that utility will see. Downstream source is my RDBMS. And precisely this Oracle. Now, from downstream source, I will I will take this information to HDFS. This is my first job. Being a Hadoop engineer or Hadoop developer, my first job is to extract this information from here and keep it in HDFS. Then only I can I can talk about analysis. How will I do that? That migration will happen, but how? So to do this migration, there we have many tools. Scoop is there, Informatica is there, DB2 is there, Spark SQL is there. Many I can use it. Some has a pros, some cons. Obviously, all the services has their own pros and cons. When we go to read the service, we'll see it. But currently, we are trying to analyze this data and understand the flow. So here, maybe I'm using a Scoop. Scoop is one utility For now, you understand as this is one utility which will extract information from here, just like a API, right? This is taking data from here and writing to HDFS. So it's creating a bridge. This is creating a bridge between RDBMS and HDFS. Here, this is my table, this is my file. So I'm converting my record from table to file. Okay. Then I will do data modeling, warehousing, and other stuff and manage that data. So flow wise, this is going to CDC. Don't care about the name. CDC is currently for changing data capture. So if I have any insert updated records, I will take it to CDC. This is not a process of Hadoop. This we have amended. This we have amended from data modeling. So if you have involved in PL SQL development or data modeling steps, warehousing management, this comes. If not, I will tell you this in project. What is a CDC? It's not a part of Hadoop, but don't worry. Changing data capture. Then SCD type 2. SCD type 2 is a slowly changing dimension. This stands for changing data capture. SCD stands for slowly changing dimension. This will manage historical data as well as near real time data. New data. So historical data and new data means this. Today, currently I'm in Pune, right? So I have my customer ID. Let's say I'm talking about the bank. So I open my account in SBI. SBI. I visit a branch code of this. Let's say, and when I visit this, they created my account, and my account is having this information: my customer ID, which is some number, then my name, then my city, then my closing balance, any X amount, date, load date, and load date is stored. Let's say I opened my account in 2015. So YY March DD. 10th March 2015, I opened my account. And if they want to store the time also, let's say this is HHMMS is 12 hours 00 minute 00 second IST. This is the current information. Now what happened? After 5 years, in 2020, I relocated from Pune, from other city. So I moved to other city. When I move to other city, what will change? My customer ID or my account number will not change because this is unique. This information will now be updated like this. It will have same record as same number. Obviously, name will not change if I change the city. It will be also similar, but this thing will be updated. This will update from Pune to let's say Bangalore. This will update, and closing balance, whatever closing balance is there by the time, by that date, then load date will be given as this load date of Bangalore. So obviously this will also change. So this is 20200101, and this is 10 hours IST. 10-hour IST. This has become my history. This has become my history, and this is my new record. If this is related to banking, obviously they will not update this information, because if you update this information in RDBMS, we know RDBMS, right? So let me create one table with this information. So create table, cust table has a cust ID, cust underscore ID, what is the data type? So this is followed by integer, Second is name. Name is followed by varchar, which is having, let me fix the length also, 10. Then we have city. City is again varchar or char or string, whatever you want to give. Again, I'll fix this to city. I'll fix this to 7. Closing balance, closing underscore balance. This is in double. Data type and load date. Last, load date. And in our database, if you know, load date, we have a date time as data type. Date time for date along with time. This is how I submitted my DDL, data definition. I have given my definition of data. Now it's time to insert it. When I run an insert into this, I'm talking about RDBMS. Insert into, and my query is starting from here to here. Insert into cust values. I'll give 24059, then name, then city, then closing balance, some amount. Let me take one number. This is 10,000 bucks. 0.00. Load date. Load date I will give now. So now means it will take today's date. Now is a function, ready-made function. It will take my system date or server date, whichever server I'm working with. Now when I record select star from table name, I can see this information. The first one. This is first. This is second. Then since I have requested my bank that I want to update it, then I will run a query, update query. I'll say update. This is my first DML, data manipulation language. This is my second DML. Value update column name. This is table name. This is my cust. Update table name. Set which value I want to change. So I want to change my city. Set city is equal to, from Pune we are moving to Bangalore. I'll say city is equal to Bangalore. Now I'll give a where condition. Where, and I'll change this date also. So I'll say comma load date is equal to now. So when I say load date is equal to now, this will take now today's date. This account we opened in 2015. This update query, banking technical people. So SBI technical people are running this query, and this record is updated in 2020. So this will have 2020 days, 20 year and followed date. Where I'll give this ID, where cust ID is equal to 24059. When I run this query, when I run this update query, I'll get this record. Right? But question here. In RDBMS, if I again want to see this information, in RDBMS, if I run a select star from table name, I'll see this record because I have updated my previous data. There is no way in RDBMS to see where this person belongs to before 5 years. Where this person was located 5 years ago, this is gone now. There is no history management in RDBMS. Once I update something, the previous record is gone. It has updated the new record. But if it is a bank and I did some suspicious activity, I did some fraud transactions within the bank, how bank will know where I was 5 years ago? So bank needs to care about my history also, so that if government of India asks from this bank that I need a record from this of this person, due to some uh, reason, right? So if they ask this information, they will have to tell 5 years ago this person was located in this city and currently he is located in this city. But if I do not manage the history, how this bank will give this information? This process is known as a SCD type 2. This cannot be managed in RDBMS, but in data modeling stage, using slowly changing dimension. Logically, if you think slowly changing dimension, we are changing dimension of our data from previous to new, but we are keeping history as well as new record also. And we're keeping this both the record, we're keeping this both the record in our main table, which is in where? Which is in Hive. And Hive is my warehouse. Hive is my warehouse. So this is one flow for historical data analysis. Now this is all the record I have kept here. I will run my query to check information. I will run a query to check data from Hive table, but I am a technical person. I know all this kind of query to submit and how to check, how to update, how to insert. Business is not a technical. Not business people, they don't know what select a star from table name stand for. So they will say, can you give me this information in more visualized form using some pie chart, some bar graph, some histogram, right? This kind of information so that I can read and make some sense. And I can pass this information to my marketing, sales, different colleagues, but not from technical side. I'll say no problem. I will give you one UI using Elasticsearch. So Elasticsearch is one tool which will give me all that visualized information in a more readable format for non-technical people, for layman people like business users. So this is one analysis which any company does. Historical data analysis, this is standard flow, guys. Okay. And why I'm calling it a historical data analysis? Because I'm taking my 100 years of data, maybe 50 years of data from here to here. I'm not analyzing the real-time data. Or you can understand this way also. Let's say today, recently we had election in Delhi, right? So in Delhi, uh, election started in 11th October. I'll take one date, 11th October 2019. Election started of Delhi Assembly, and election started at 9 a.m. So people started voting at 9 a.m. They started voting, and from 9 a.m. to 6 p.m., or actually it goes from 7 to 5, but I'm just taking one range. 9 a.m. to 5 p.m. election happened. The event gets completed by this time, 5 p.m. Now, when I started analyzing or reading this data, how many people have voted for party A, party B, party C? Three parties are there, let's say. So how many people have voted to how many people? I am doing my analysis at 7 p.m. Look at the scenario. 9 a.m. election start, 5 p.m. election done. Stop. I am doing my analysis after 2 hours. This is what? This is history. This is not real-time analysis. This is a historical analysis because you are doing after 2 hours. If you're doing after 1 hour also, if you're doing after half an hour also, I'll say it's a historical analysis. It's not a real-time analysis. Real-time analysis is this. Election is started at 9 a.m. This is case 1. This is case 2. Election started at 9 a.m. And I have calculated, or I did my analysis from 9 a.m. to 9:30. So how many people have voted? How many people have voted from this time to this time? Let me actually create a range here. So from 9 a.m. to 9:30, which means I have created a slot of half an hour, that after every half an hour I'll make my count updated. I'll, I'll first count it since this is first cycle. Then I'll keep doing this. Then I'm keep doing this 9:30 a.m. to 9:30 a.m. to 10 a.m. This is my second counting. Likewise, I'll keep doing this, and my last counting is happening from 4:30 p.m. to 5 p.m. Because when I reach to this time, my all previous cycle is already done, and I'm aggregating it. I'm not separately counting, I'm aggregating it. So here, if I say A is a party, and A party has total got 12 votes. So I'm not separately saying from 9:30 to 10, A has again got 4 votes. I'm saying 12 plus 4, 12 plus 4, which is 16 vote. And likewise, I'm aggregating it. So by the time this event gets completed, 5 p.m., I get to know how many number of people have voted for party A, how many people have voted for B, how many people have voted for C. If people have voted 112 votes for A, people have voted 30,000 for B, and people have voted 24,600 for C. So I know at 5 p.m. immediately I know, okay, who is the winner? This party B is a winner of the Delhi Assembly election. This is how real-time analysis works. This is your real-time analysis. So we use this term, but it's not 100% real time at first case, guys, because whatever you see, you watch any live telecast, any broadcast, some football, cricket is happening, somebody is speaking, right? Nothing is 100% real time because nothing can travel with a light speed, right? So this is a near real time. We always say there are 2 second, 5 second gap is there, right? So it's always referred as a near real-time data analysis. The 90% data, 80% data can be real-time, not 100% data can be real-time. Even recently, we have a moon mission in India, right? They also was a 5 second gap between that because from Indian satellite to sending one radio frequency to moon, Vikram lander, and again coming back from Vikram lander to moon, that was 2.5 second sending information from Earth to moon and 2.5 second acknowledgement from coming to there. So there was 2.5 second, 2.5 second, which was 5 seconds in total. This is a near real-time analysis. In near real-time data analysis, you don't care about data, you care about the time. You care only, you say that I will take care of 30-minute data at one cycle. Now, if this is very frequent, if this is happening in every 5 seconds, so you can say that after every 5 seconds, I will do my analysis. Currently, what is your interval? What is your window interval? Window interval is half an hour. This is up to you. I've just given one example. When we go to Spark streaming, actually Spark does that job. Spark will handle this. So I'll create a now second analysis for real-time analysis. How real-time thing will work. This is a second case. Real time, and as I have written earlier, it's near real time. Let me correct it. Near real time data analysis. So what we do here, it is going to web server. One thing we will scrap from the previous image. We don't need this downstream now. We have a web server which is upstream, and from this web server, we are directly taking this data to where? We're taking this data directly to MQ, and that MQ, the tool name is Kafka. We have this Kafka thing in our course. So Kafka will take this. Kafka has a producer and consumer concept. So Kafka producer, I will relate this flow with a Netflix just after this flow because Netflix uses Kafka. Uber uses Kafka to connect their riders and drivers. Kafka producer, then Kafka queue, then Kafka consumer. This Kafka consumer is nothing but Spark streaming. This is nothing but Spark streaming. Spark streaming will analyze this data, process it, and once this is processed, where will it store this? In a low latency databases. HDFS is designed for high latency. Then how many options we have for low latency? All NoSQL, which is HBase and Cassandra. And then again, this data we are accessing from some UI or dashboard and giving this information to our business people. This is how your real-time analysis works. Now, how this Netflix is working. So I have account, let's say I have account here in Netflix, this. And this account is having multiple screen, right? We have 3 screen accounts, 2 screen account based on the amount. So let's say this is having 3 screen. Now, how one account it can give 3 different information. So my one friend, I've shared this account information to one of my friend who is in USA. He's watching something from there. Let's say he's watching some thriller series. Me watching from India. I'm watching some uh, animated. And third person is also in India. And this guy is watching some movie. There is just one. This is what? This is your producer. This Netflix has one server, and that server is behaving as a producer. So it is producing the data, but these are what? These are different customer, or I can call as a consumer. Consumer number 1, consumer number 2, consumer number 3. And then they are seeing all 3 different data all coming from one producer. This whole picture, holistic view is what? One producer, many consumer. One producer, many consumer. It can support multiple producer, multiple consumer also. It can support multiple producer, one consumer also. So this whole thing can be done by your Kafka. Kafka helps to perform this. It balances the load. It balances the load, and it will give you option for one producer, one consumer, one producer, multiple consumer, multiple producer, one consumer, multiple producer, multiple consumer. So all that different combinations we have using Kafka. Uber uses the same thing. They connect you with your driver using this Kafka. So when you request, let's take example of Uber also, because when we relate with a real-time application, things are more clear. How we are using this. So currently, what is the time? It's 10:59. Okay. So 10:59 you requested, 10:59 a.m. you requested a cab and you want to travel from your location, let's say Kharadi, you want to travel to Hadapsar. When you requested at 10:59:00 a.m., your request is not immediately accepted, right? Your request takes time. Maybe 10 seconds, 20 seconds, 30 seconds. If they're not able to find out the driver, you will have to re-request again. So they will increase your range. Maybe they're searching first in 3 kilometer radius. If you're not able to find out, they will increase this range to 5 kilometer. And likewise, they keep increasing. The moment you keep searching, this is getting increased. So 10:59 a.m. Kharadi to Hadapsar. If your request gets completed at 10:59:35 a.m. and just a sec, 10:35 a.m. and you made a request at 10:59:00 a.m. So where your 35-second data goes, where your 35-second data is going, because if you check between these two, there is 35-second your request accepted. This 35-second data is going in Kafka. To connect, Kafka is just giving a pipeline, just a pipeline connecting from you to other server or other consumer.